In the equilibrium chapters of a classic Gen Chem class, you run across a lot of different calculational problems, and they tend to be in two major categories. One of them is this, here are some concentration information. What is the value of the equilibrium constant? The other type of question is, here's an equilibrium constant, calculate the concentrations at equilibrium. Okay, and those are pretty standard type problems. You see them throughout the equilibrium chapters. There's one type of problem, and this is one I wanted to look at today, that sometimes gets overlooked until students hit it somewhere in the end of chapter problems in an equilibrium chapter and aren't quite sure what to do with it. And this question is, are you at equilibrium? Does this container contain a mixture that is at equilibrium or not? Okay, and so it's not calculate an equilibrium constant. It's not use the constant to calculate new concentrations. It is simply, is this combination of things at equilibrium or not? Technically, it's called a reaction quotient question. Reaction quotient. And I'll get to that term in just a moment. But the essence of the question is, are you at equilibrium? Okay. And if not, do you have to shift from reactants to products or products to reactants in order to get to equilibrium? Okay. So to illustrate what I mean, let's take a look at a reaction quotient type question. So here's the text of it. And notice right there in the text of it, are you at equilibrium? If not, which direction does it have to go to get to equilibrium? The reaction is this one. Okay, pretty standard one in equilibrium studies in general chemistry. Okay, dinitrogen tetroxide and nitrogen dioxide. Now, before you do anything in an equilibrium chapter, I always think it's just a vital idea that you write down the equilibrium constant equation. Remember, it changes, it looks different depending upon the reaction, but it always has the same essence, products over reactants, each raised to their stoichiometry coefficient. Here, going to be NO2 is in my numerator, and I square it because of the coefficient of 2, and 2O4. Okay? And now we are in this problem specifically told it has a value 0.21. Okay? A number less than 1, this is a reactant favored equilibrium. Okay? The N2O4 is the favored side at the temperature it was measured at, 0.21. I think in the problem it says 100 degrees C. Okay? Now, here's the meat of the problem. They tell us that we have a mixture of these two, okay, that contain. We do note that the problem does give us specific values of the concentration of nitrogen dioxide and dinitrogen tetroxide. And I had them written down over here. Nitrogen dioxide, 0.55 moles per liter, and the N2O4, 0.12 moles per liter. Okay? And the question they're asking is, does a container that contains these concentrations is at equilibrium? Okay? Now, the way you answer it is pretty straightforward, but there is a critical point to note here. When you are working with an equilibrium constant equation like that, I tell my classes, you are allowed to only plug in equilibrium concentrations. You must be absolutely certain that the concentrations you plug into this equation are equilibrium concentrations, okay? Not initial concentrations or anything else. They have to be equilibrium concentrations. That's what an equilibrium constant is based on. Note the way this problem is written. You don't know if these are equilibrium concentrations, okay? In fact, that's the whole point of the question. Do these concentrations produce, an equilibrium mixture or not? The way you answer it is you do this calculation, but the way the textbooks will write it, and I actually kind of agree with it, is to not say just plug it into the equilibrium constant equation. It is to write the reaction quotient equation. Now, it seems to be, for a lot of students, it seems to be, well, hell, that looks a lot like this one, and it is. But the point is, you are allowed to plug any old set of concentrations into a reaction quotient. Okay, where you're not allowed to plug in just any concentrations into an equilibrium constant equation. This is more restrictive than reaction quotient. Now, doing that allows us to do the following. Okay, I put 0.55 on top and square it. And I put the 0.12 on the bottom, and I do my magic little calculator business, and I find that comes out 2.5. Okay? Now that is the core of the problem right here. Are you at equilibrium? Yes, only if the reaction quotient and the equilibrium constant produce that value, 0.21. If the reaction quotient produces anything else, you are not at equilibrium, and we are not at equilibrium. So we've answered the first question, okay? Are you at equilibrium? No, we're not. The second part of the question is, okay, if you're not at equilibrium, which way do you have to go? Do you have to go from the left to the right side, or do you have to go from the right to the left? Remember, this is an equilibrium. It's a reversible reaction. It can go, under the right circumstances, either way, okay? And so that's what makes it an interesting type of equation to deal with, an interesting reaction to look at. So we have to decide what this 2.5 is telling us relative to the 0.21, okay? Because what we now know is these concentrations are not equilibrium concentrations. But do they represent, is the balance here too much dinitrogen tetroxide, too much reactant side, left side is the way it's written, or too much NO2, nitrogen dioxide, the product side as it's written here. Looking at it here, I produce a value, a reaction quotient, greater than the equilibrium constant. That means that my reaction quotient, the numerator, is too big. This 0.55 is too big. I have to actually find, 0.55 is too large. A value smaller than that, when plugged in, will bring the 2.5 down to 0.21. The 0.55 is too large. The concentration of NO2 is too large. In other words, this is too large a concentration. There is too much of this one, okay? And that means we're going to have to go from the NO2 side, the right side, to the left in order to bring this concentration down, bring the N2O4 concentration up, until we find the magical values that will multiply and divide as written to produce 0.21, okay? So it has to shift, as it's written here, right to left. And that is often the way these things are asked. Does it have to shift to the right? Does it have to shift to the left? It has to shift from the right to the left side. It has to shift left in order to bring this mixture into equilibrium. Okay, subtle type question actually, and like I say, it's one that's commonly overlooked because it's not, the main question in an equilibrium chapter, but they do pop up from time to time, where the point of the question is not, what is the concentration at equilibrium, but simply, are you at equilibrium? You answer it by taking your concentrations, plugging them into the reaction quotient, which yes, bears a suspicious resemblance to the equilibrium constant equation itself, and figure out, does this value match that value? If not, then you're not at equilibrium, and you have to figure out what you need to do, more right side, more left side, in order to make that number work out here. Textbooks will often have like a little cartoon version of this and that some students feel more comfortable just memorizing. If your reaction quotient is less than equilibrium constant, the following has to happen. If reaction quotient is greater than equilibrium constant, like it is here, the following has to happen. So here is a picture of the one that our current textbook uses. Whatever way you feel more comfortable doing this, either memorizing what to do when the reaction quotient's larger or smaller than the equilibrium constant, or just kind of doing a little bit of logic. This number means the numerator is too big, the numerator is this side, therefore I have to have less of this, and that means I have to shift from the right to the left. However you do it, as long as you come up with the right answer. So, hope that helped, and talk to you later.